In the last video, we introduced the zeroth law of thermodynamics, explored the concept of having the same temperature, and looked at how heat transfers occur at a microscopic scale. So going from there now, we can transition into the first law of thermodynamics. And this often gets written as delta E thermal equals W plus Q, or a lot of books will write Q plus W, either way. So this is saying that the change in thermal energy of a system will be equal to the work done on the system plus, so think like Joule's paddle wheel thing, plus heat transfers into the system. Think Bunsen burner type things, where the hot gas molecules are colliding directly from the Bunsen burner, colliding directly with the beaker and transferring thermal energy that way. So for signs, if the change in thermal energy is positive, that will correspond to an increase in internal or thermal energy. And if it's negative, then we have a decrease. If Q is positive, that means that the system gained heat. And if it's negative, our energy in motion, our thermal energy in motion, heat, system will have lost heat to the environment. So, and finally, oops, let me not go up too far. For our definition, if the work is positive, this means that work is being done on the system by the environment. And if work is negative, that means that the work is being done by the system on the environment. Now these last two here you need to be super duper careful about. You definitely want to check the signs on work. It turns out that the field of thermodynamics doesn't belong to any one particular scientific discipline. There's just a lot of subjects called thermodynamics that tend to overlap across them all. And one of the fields is engineering. Engineers are usually more interested in the work being done by a system rather than being done on the system, because you're trying to extract useful work from, say, an internal combustion engine or something like that, where the expanding gases in the piston will eventually cause the car to move forward or something like that. So from their perspective, it makes more sense to define work being positive if the system is doing work, and negative if the environment is doing work on the system. Physicists, on the other hand, not entirely universally in thermodynamics, but as a general philosophy, tend to have transfers into a system being positive and out of a system being negative, regardless of what kind of a system it is or what kind of a transfer we're talking about, just as a general guideline. And other fields will have other approaches on that. However, there's enough crosstalk within the world of physics that there's not universal agreement on what sign W should have. I'm going with the one that's the most common in most intro books, but there are certainly even intro level books where these signs have been defined the other way. And if they've been defined the other way in those books, the first law will be written as Q minus W. So it's still the same first law of thermodynamics. There's nothing different. It's just the definition of whether work is positive or negative is different. And honestly, I pretty much find it to be a pretty even crapshoot in a lot of texts which definition is going to be used. So whenever I'm looking at some book's treatment of thermodynamics, the very first thing I do is flip to the page where they define the first law, just so I can see whether they write W plus Q, which is following this definition, or Q minus W, which is where they're following the definition where the signs of work are reversed to the more engineering focused definition. So just as a point of caution here, I'll be adopting this definition where positive work is work done on the system and negative work is work done by the system. Now, it'll turn out that in the history of developing the laws of thermodynamics, there was a period of a good couple of decades where lots of seemingly wildly disparate statements about thermodynamics were shown to all boil down to being either equivalent statements of either the first or the second law of thermodynamics. And in a upper level undergraduate physics course, a physics major will spend several weeks learning how to take any particular statement and get from it any other particular statement of the first or the second law or whatever. I certainly won't be doing that here, but I will state some of the more useful equivalent statements because they sound so wildly different. Sometimes it's more useful to have one of these other statements when thinking about a problem. So here, an equivalent statement of the first law of thermodynamics, and most of these other statements are usually statements of impossibility. So here's one. It's that it is impossible to construct a perpetual motion machine of the first kind. Yes, there are two kinds of perpetual motion machines. So I'll call this perpetual motion machine first kind, like that. A perpetual motion machine of the first kind is a machine that runs forever and does useful work. So when you go into the darker, scarier corners of the interwebs, this is all of the free energy. Things that you're apt to see. And of course, there are plenty of other signs that should be warning you that your BSO meter should be deflecting a little bit. Usually they'll say, the secrets the man doesn't want you to know. Just send me, a couple of Bitcoins and I'll send you the plans for this machine that will allow you to be independent of energy forever. It'll just run and give you everything you need. Okay, so yeah, it's totally reliable that this person that you're sending Bitcoin, untraceable cryptocurrency to, some random Gmail address. I'm sure they're totally legit, don't you think? Yeah, I thought so. So, and also the whole thing, that they don't want you to know. Whenever someone says they, the great unspecified they don't want you to know something. Again, your ears should probably be perking up and going, yeah, right. What's going on here? So, anyway, but just in case those usual things weren't enough, you now also know that what they are touting violates the first law of thermodynamics. You might ask, how so? Well, okay, if you're going to have some sort of a perpetual motion machine, or any kind of machine actually that's going to do useful work, it has to run in some sort of a cycle. Now, this cycle could be incredibly complicated. It could take a very long time to run, but it's got to go through some sequence of steps and then end up back where it started from. So that's the thing, is when you end up back where you started from, you'll be back at the same energy, at the same temperature. Whatever working substance you've got in your device, once you get through however many steps you're taking to extract energy, to extract work from it, eventually, if it's going to be something that will keep running, it's got to loop back to where it started from, and then it'll be back at the same temperature. And this is the big deal. Since you're at the same temperature, we saw that the temperature is directly proportional to the thermal energy of the working substance here, the gas or whatever. So this means that at the end of a cycle, the change in the thermal energy is 0. Okay, so that makes delta E 0. Since it's a perpetual motion machine, you're not burning any fuel or anything like that, so there's no heat transfer. That's 0. Well, you're left with work equals 0. There you go. Sorry. Now, you may be wondering what a perpetual motion machine of the second kind is. That turns out to be one that just literally just runs forever, but doesn't do useful work. That one turns out to violate as you might guess, the second law of thermodynamics. This one violates both the first and the second, but a perpetual motion machine of the second kind, which we'll get to with the second law of thermodynamics, only violates the second law of thermodynamics, but not necessarily the first. All right. So with that, you're going to start thinking about extracting useful work from thermal processes. And something that's really useful to that end is something called an energy transfer diagram. So we can start by imagining something like, say, putting a copper rod here. And let's say we've got a Bunsen burner burning over here. And again, it's a flame because I labeled it as a flame. There we go. And over here, let's say you've got a melting ice cube. So, it's an ice. That's just all awful. Let's try that again. There. So here's your ice cube melting. So as the flame is burning here, the gas molecules in the flame are colliding with the atoms of copper in the copper rod. So the gas molecules will, on average, lose kinetic energy. The atoms over here will be gaining kinetic energy. So they'll be vibrating in their lattice positions more violently. So there will be a transfer of heat. Oops, I want red here. So it'll be a transfer of heat from the flame into the rod over here. We'll call that one Q hot. Now, as we go down, if we look over here, so we're going down, this means that we're going to be making the temperature of the rod hotter over here than it is over here. So if I look at any adjacent couple slices of the rod, the atoms over here will be moving faster than the atoms over here in the lattice. So adjacent atoms in the lattice will continue to have these elastic collisions, causing the average kinetic energy of the atoms here to drop again a little bit, and these to go up. Now, of course, the flame will then go, and by these collisions replenish what the atoms here lost, but we've moved thermal energy down the rod. So there. And then eventually we end up over at the ice cube. Now at the ice cube, what's happening is the atoms in the copper rod are vibrating more rapidly. They have a higher average kinetic energy than the water molecules in the ice. But it turns out that you'll start, if say it's near the melting point, you'll start to break the bonds that are holding the water molecules together, and that causes the meltage. So anyway, same deal. The average temperature here is lower, average lower thermal energy. So we'll have a heat being transferred into the ice. We'll call that QC for Q cold. So now these two things here, usually when you're starting to talk generically, we'll call this flame a hot reservoir. So this is basically something that we can just keep drawing thermal energy from that's at a high temperature in this case, without significantly changing the temperature of the reservoir. So this could either be like a flame here where because of combustion, it's always going to end up being the same temperature. Or say with the ice cube here, as long as you're melting water, you're using energy. The thermal energy is going into breaking the bonds between the adjacent water molecules, but it doesn't change the average kinetic energy. It's just changing potential energy. So we would call this one the cold reservoir. So in this case, both here, just because we're continuing to do combustion, we can maintain a temperature of, we'll call it T hot. And here, because of the details of ripping apart the bonds within the ice cube, we'll say that the temperature there is T cold. And the idea with the reservoir is these temperatures stay basically the same. Now, another possibility would be, say, as an example of a hot reservoir, we might think of an Olympic swimming pool. You go throw a small chip of ice into an Olympic swimming pool, that chip of ice is going to melt, and the temperature of the Olympic swimming pool will go down, but it's probably going to be in like the 6th or 7th decimal place. And so a lot of times you can approximate things like that as a heat reservoir as well. So it could either be a very large object where the temperature won't change much, or it can be an object where the chemistry of the situation guarantees a particular outcome. So anyway, to look at the energy transfers here, this copper rod, if we're being more generic about, we call this the working substance that we're looking at. And so when we draw a energy transfer diagram, usually what you do is you draw two boxes for the reservoirs. T hot, T cold. So this is your hot reservoir. This is your cold reservoir. You draw a circle for the working substance. And then in this particular example, all that's happening is heat is being transferred from the hot reservoir to the cold. So remember again, heat is energy in motion. So Whenever we're having these collisions from this interface to that interface, we call that a heat transfer. So I'll be Q hot there. We always draw it like with two lines with an arrowhead, like that. And then we're transferring out of the working substance into the cold reservoir, so we would just label that Q cold, like that. All right, that's not a particularly exciting one. So we'll get to some others here. So I'll start by doing one that turns out can't be drawn. Or, well, it can be drawn, but it's not a legal one. So this one turns out to violate. So all I'm saying is just because you can draw it artistically doesn't mean it can happen in practice. So as in here, we're showing that the heat transfer is running in the other direction. And if there's no work being input or output from the working substance, which I haven't shown you how to draw yet, this turns out to violate the second law of thermodynamics. Oops, let's try that again. But, so you could draw it, but just because you draw it doesn't mean it can happen. So you gotta have a little bit of care with these. And then you can sometimes get weird things. You always draw a hot and cold reservoir, even if that isn't appropriate. So here, I'm going to be drawing Joule's experiment. So again, we'll draw a hot reservoir and a cold reservoir, but it turns out there wasn't actually a hot reservoir. Remember, Joule's experiment was that paddle wheel contraption that did work on the water. The water is our working substance here. And it's also our cold reservoir. So here what you do is you draw in, usually do it just as a single arrow here. You do work on the working substance and it gets rejected as heat to the cold reservoir. And there is no heat transfer from the hot reservoir. In fact, there isn't even one. So this would be Joule's experiment, or work is converted completely to heat. So that's another more weird example. But normally the sort of thing that you're thinking about when you're drawing these things is something called a heat engine. We'll also worry about refrigerators in a bit. So in a heat engine, you will have a hot reservoir, and you'll have a cold reservoir, and you'll have a working substance. This is usually going to be like a gas in a piston or something like that. You will extract heat from the hot reservoir, reject heat to the cold reservoir, and the difference will go out as useful work. Now I'll call this W sub out to note that this is the work being extracted. So I'm kind of putting my engineer hat on for just a moment here. Okay, so by the first law of thermodynamics, delta E thermal equals Q plus W. All right, since this thing it's an engine, so it's something that's running in a cycle. Since it's running in a cycle, we can set delta E thermal to be 0 over a cycle. During that cycle, what's going to be the net heat transferred in? Well, we extracted Q hot into the system, so that's an inbound transfer, that's positive, but we also rejected Q cold to the outbound system. And then this would be equal to, this W here is the work being done on the gas, But here we want to get the work done by the gas. And so that's going to be equal to the negative of the work done on the gas. This will be minus W. So we get that the work out, sorry, minus W out. So we get that the work out that we extract out will be equal to Q hot minus Q cold. Okay, that makes sense. So if we want to define the efficiency of our engine, so the efficiency here, this is just a lowercase e. All of our figures of merit in physics are almost universally what you get over what you had to pay. So what are you getting out? The useful work. What are you paying? Q hot. Q. And the reason I say that is, this is going to represent, say, the fuel that you burn to run your car engine or whatever engine you're thinking about. That's what you burned. What goes out the tailpipe or the smokestack or whatever, that's going to be Q cold. So for any heat engine, that will be equal to the work out over Q hot. Now from here we have that the work out is Q hot minus Q cold. So we can also write this as the efficiency for any engine is equal to 1 minus Q cold over Q hot. So this one's really useful, but occasionally you'll like this one. So these relations are true for any engine. Now, when we get into the second law of thermodynamics, I will mostly be asserting and kind of doing a hand-wavy justification. There is a maximum possible efficiency. This gets called the Carnot efficiency of a system. And this has been shown to be equal to 1 minus T cold over T hot. So this is our maximum possible efficiency. When we get into doing the second law of thermodynamics, one of the equivalent statements of the second law will in fact be that no heat engine can have an efficiency greater than this Carnot efficiency. So when you're looking at your energy diagrams, you get the efficiency by either looking at the work out in Q hot, or you can get from looking at Q hot and Q cold. But you then also, to make sure that it's actually a legal diagram, you have to make sure that said device is not more efficient than this Carnot efficiency. Okie dokie. So this leads to one variant on a heat engine. That's a heat pump or a refrigerator. Heat pumps are heat engines that are run backwards. So here, the work is being input into the working substance. So we'll say work input like that. And now, unlike before, when I said that we couldn't draw the heat arrows flowing up, you can if you're doing work to make that happen. So a heat pump or a refrigerator is a device that does work on some working substance, usually a gas, to move heat from where it's cold to where it's hot. So in the opposite direction of where it spontaneously wants to flow. And it turns out that you can move, as we'll see in just a second, you can move more heat than the work going in, and that is actually okay. But just to tie it into, say, like your refrigerator at home, just to give some example of how this is working, the inside of the refrigerator is the cold reservoir. So think your leftover sandwich. Now, in the refrigerator, there is a compressor. So it does by letting gases compress and expand in a clever way, you can move heat from your sandwich to the hot reservoir, which is wherever your refrigerator is located. Home, the break room, whatever. And the work that's being done to do this is being done by an electric motor that's attached to that compressor. So when we're trying to think of our figure of merit here, and here usually it's called COP, and this stands for coefficient of performance. Again, it'll be defined as what you get over what you had to pay. Oops, yeah, let's try that. There we go. So what you get here is the heat that you're removing from your leftover sandwich. And quite literally what you had to pay was the inbound work. That's going right off your electric bill. And similarly, you can show that there is a maximum possible coefficient of performance. So again, so this would be for a Carnot refrigerator here. And you can show that that maximum possible value is T cold over the difference in temperature between the reservoirs. So you don't have to, if you go and take a look at this, and here you want to be careful, you do have to work in absolute temperatures for all these relations. So convert everything to kelvins. But here, let's say you're thinking about your refrigerator. Well, let's think about your freezer just because it'll be easier to think about. Your freezer is going to be somewhere around about negative 10 degrees C or something like that. So it'll be like 263 Kelvin. Your room is, the room that the freezer's in is at room temperature, which is around 300 Kelvin. So if we say, instead of 263, let's say 260 for just nice round numbers. Put 260 in the numerator, 300 minus 260 in the denominator is just 40. So that's going to be a coefficient of performance of about 6.5. So you can move 6.5, at maximum, you can move 6.5 times more heat out of your leftover sandwich as energy you put in to make that happen. So it's just it's not violating anything because you're just doing work to move heat around. Now, if you tried to move more than 6.5 times that much heat, that would violate the second law of thermodynamics.